Welcome back to the FE exam review series where we focus on problems built around fundamentals that will help you pass your FE exam. Today's problem is based off of section K in the thermodynamics subject. I highly recommend you try the problem for yourself before watching this video solution, and you can do that using the first link in the description below. I hope you tried the problem. Let's get into the solution. It says during a combustion process, hexane fuel, which is C6H14, so it's a hydrocarbon fuel, it burns with 100% excess air. Additionally, the molar mass of air and hexane are shown above. The air to fuel ratio is most nearly. Okay. Essentially, what we're looking for in this problem is that air to fuel ratio. And we know that we're not dealing with just stoichiometric combustion. What we have is 100% excess air. And I'll explain exactly what that means. Essentially, the air to fuel ratio is exactly as it sounds. It's the mass of air divided by the mass of fuel. Now, we can find the mass of air by taking the number of moles of air multiplying the molar mass of air. If you look at the units here, it makes sense that we're using that kind of formula here. Number of moles is like kilomoles, and the molar mass is kilograms per kilomole. So the kilomoles cross out, we're left with kilograms. That equation makes sense. And the number of moles of fuel divided by the molar mass of fuel. Okay, so that means if we're able to find this correct number of moles of air to number of moles of fuel, we already have the molar mass of air and the molar mass of fuel. We'd be able to find our answer. How we find that molar ratio that we need is by looking at the stoichiometric combustion equation and then incorporating the excess air afterwards. If we write down exactly what the combustion equation is, for hexane, we have some amount of fuel, C6H14, is burned with some amount of air. Now, air is just oxygen plus 3.76 nitrogen. Now, why is it like that exactly? Air is 21% oxygen and 79% nitrogen. Someone didn't like working with these decimals here, so they multiply by 1 over 0.21 here. And if you multiply that ratio, then you get what you see above, right? The 1 plus 3.76 and 2. Okay, what that's going to produce is some amount of carbon dioxide, some amount of water vapor, and some amount of unburnt nitrogen. This is for the stoichiometric combustion equation, so theoretically, this is the amount of air we need. If we wanted to modify this to allow for some amount of excess air, then all we do is multiply this by a factor, 1 plus the excess air fraction. We multiply that by the amount of air that we have, and we'd gain a term on the right-hand side, which would be some amount of unburnt oxygen, that excess oxygen term. Okay, so in terms of what we need to do, we need to take the number of moles of air, which is 1 plus the excess air fraction, multiplied by our stoichiometric coefficient. We're going to take that and multiply it by 4.76. The 4.76 is there because we have 4.76 moles of air. There's 1 mole of oxygen and 3.76 moles of nitrogen. So overall, that's 4.76 moles of air. And we have those two factors in front. We take that, which is the number of moles of air, multiplied by the molar mass of air, which is 29. It's in the givens here. We take that value and divide it by the number of moles of fuel. We're going to assume we have 1 mole of fuel here. So this is just a 1 here. And the molar mass of fuel is just 86.177. So if we can find our stoichiometric coefficient here, we know what our excess air fraction is, just 1, right? 100% or 1. So all we need to do is solve for that stoichiometric coefficient. And we do that by looking at the combustion equation without any excess air. So I'm going to go ahead and remove that. that excess air. And we're just going to solve this just doing stoichiometry. Before we finish up the video, if you're learning something and you enjoy content like this, consider leaving a like and subscribing. It really helps support the channel. Additionally, if you're prepping for the FE Mechanical exam, you're looking for resources that will help you pass the FE Mechanical exam, consider checking out my software, FE Interactive. You gain access to practice exams, which are timed, as well as review and improve sections to help you isolate specific pain points or weak areas that you have. You have access to calculator tips for your TI-36X Pro, as well as detailed analytics, which ties all of these sections together. You can see you have data for improve and review, as well as test. And for each test, you have a scorecard. You can see the detailed scorecard here, which you can organize in terms of performance. And that's a super useful feature because you know which sections to isolate. You also have access to full solution manuals, so you can go ahead and review and really understand what exactly is it that you're struggling with. Additionally, you can look at the data overall, and you can see what your top 3 and bottom 3 subjects are in terms of overall performance, and you can use that to target the different sections. I'm confident that FE Interactive will help you pass your FE Mechanical exam. You can use the third link in the description below. It's a referral link to get 2 months of access for $29.99. Let's get back into the problem. So we're going to start with the carbon balance. We have 6 carbons on the left side. And how many carbons do we have on the right side? We have 8 carbons on the right side. So immediately we know that coefficient A is equal to 6. What about the amount of hydrogens? The amount of H's that we have? What we see is that we have 14 hydrogens on the left-hand side. What about the right-hand side? We can go through and count it. We have 2B amounts of hydrogens on the right-hand side. So that means B is equal to 7. And what about oxygen? Oh, how many oxygens do we have? We have 2 times the stoichiometric coefficient. That is the amount of O's on the left-hand side. What about on the right-hand side? We have 2A plus B. Now we know what A is and we know what B is since we just performed our stoichiometry. A was 6, B is 7, and we can solve for our stoichiometric coefficient here, which is 12 plus 7 divided by 2. That's 19 over 2. If we go ahead and plug in that 19 over 2 value here as our stoichiometric coefficient, we see that 19 over 2 and this 2 from the 1 plus excess air fraction is going to cancel. We have a 19 times 4.76 multiplied by 29 divided by 86.177. The units on that is kilograms of air per kilograms of fuel. And it turns out to be around 30.43. Okay, so this is the answer. Let's go ahead and check that answer. 30.43. We did get it right. Let's quickly review what we did. We were looking for the air to fuel ratio. That's a ratio of masses. It's the mass of air per unit mass of fuel. What we did was we wrote down the stoichiometric combustion equation as well as the actual combustion equation with excess air. The only difference was that the actual combustion equation had the 1 plus the excess air fraction, which was 100% for our case. Overall, what we were seeing was that in order to find the air to fuel ratio, we really just needed that stoichiometric coefficient. So we could just do that by balancing the stoichiometric combustion equation. We found this A and B, which are unknown coefficients, in front of the carbon dioxide and water vapor. We used that to find our stoichiometric coefficient, and then we plugged it into that mass of air per unit mass of fuel, and we were able to find what the air to fuel ratio is. So it was choice C. If you enjoyed the video, please consider leaving a like and subscribe. Thanks for watching. I'll see you in the next video. Goodbye.